Let's study 9th standard ICSE physics numericals of exercise 5B and 5C. Let's start with exercise 5B. The first few sums are pretty challenging. First, the density is given as 8.83 gram per centimeter cube, and we have to convert it into kilogram per meter cube. So what do we do here? We multiply by 1000 and we get this answer. The third sum, the density of iron is given in kilogram per meter cube, and they want the answer in of relative density. So there are two ways to solve this. One is use the formula of relative density, that is density of iron upon density of water, which will be 7800 upon 1000. Or we can just convert the density given in gram per centimeter cube, because then if we get rid of the unit in CGS system, what is left is called the RD. Next, the fifth sum. Calculate the mass of a body whose volume is given and relative density is given. First of all, from relative density, we can find the density. If RD is 0.52, that means density is 0.52 gram per centimeter cube. Note that the volume was given as 2 meter cube, that was in SI unit. So it becomes imperative for us to convert the density also in SI unit. And then we know the formula of mass is density into volume. We get the mass in SI unit. Next, the seventh sum. A piece of stone of mass this much sinks to the bottom in water. That means it is completely submerged. And the water level rises from 30 ml to 40 ml. So the water level rises by 10 ml. So isn't the volume of the displaced liquid equal to the volume of the immersed solid? That means the volume of the stone is 10 ml. That is 10 centimeter cube. 10 ml is nothing but 10 centimeter cube, because 1 ml is 1 centimeter cube. Know the conversions. So now I have the mass as well as the volume, so I can find the density, because density is equal to mass upon volume. I've used a rho symbol for density. We get the answer of density in CGS units. If you hide the CGS units, what is left is called the RD. Next, the ninth sum. The mass of a body, 70 kg, when completely immersed in water, displaces 20,000 centimeter cube of water. So in air, the weight is 70 kg. In water, obviously, it will be less than 70 kg because there is some upthrust, but we don't know how much. All we know is that the volume of water displaced is 20,000 centimeter cube. So first of all, write the data always. Mass is given as 70 kg. So the weight in air, which is referred to as W1, is 70 kgf. Now, volume of water displaced is 20,000 centimeter cube. Also, the weight of water displaced is always equal to the upthrust. Yeah, remember this equation, that the weight of liquid displaced is equal to the upthrust is equal to the loss in weight of the object. And the formula of upthrust, we know it is V rho G. Even if you say the formula of weight is also V rho G, because V into rho is the mass and mass into G is always the weight. But notice here the rho is of the liquid, that is of water, because we are finding the weight of water. Since volume is given in CGS units, the density of water in CGS unit is 1 and G's value is not given, so we will take it as 1. So the answer is not in SI unit, it is in GF unit, 20,000 GF. So the weight of the object was 70 kgf and the upthrust acting on it is 20,000 GF. So what will be the loss in weight? Well, if this is in kgf, please convert this also in kgf, which is 20 kgf. So the loss in weight is of 20 kgf. And what will be the new weight now? It will be 70 minus 20, which is 50 kgf. This is the new weight in water, which we take it as W2. Next, they've asked us to calculate the RD. Well, we have the direct formula of RD, W1 upon W1 minus W2, where W1 is the weight in air and W2 is the weight in water. So just substitute the values and we get the RD as 3.5. Please mark this 9th sum as IMP. Also the 11th and the 16th sums, mark them as IMP. Now the 11th sum. So in the 11th sum, a solid weighs 32 GF in air and 28.8 GF in water. Obviously it will weigh less in water because there is an upthrust acting in water. So the new weight in water is 28.8 GF. That is also called the apparent weight in water, or the net force in water. What is the loss in weight here? Think about it. Well, it's 32 minus 28.8 GF, which is 3.2 GF. So what is the upthrust acting on the object? Think about it. Well, the upthrust acting is equal to the loss in weight, so it is 3.2 GF. And what is the weight of water displaced? Well, weight of water displaced is also 3.2 GF. So remember, the weight of liquid displaced is equal to the upthrust by the liquid is equal to the apparent loss in weight of the object. But what they have asked first of all is the volume of the solid. They have given us the weights and they have asked us to find the volume of the solid. How do we do that? Well, you know that the volume of the solid, since it is completely immersed, the volume of the solid is equal to the volume of the water displaced. And the volume of the water displaced is numerically equal to the weight of the water displaced, because density of water is 1. So volume is equal to the weight of water displaced. And how much is the weight of water displaced? It is nothing but the loss in weight which we see. So by that logic, we can directly write the formula that volume is equal to W1 minus W2, which is the original weight minus the new weight. This is the loss in weight. This difference is the upthrust. This difference is the weight of the liquid displaced, which is equal to the volume also, because density of water is 1. And it is also equal to volume of the object, because volume of the object is same as volume of the displaced liquid, because it is completely submerged. Note that though we are writing W1 and W2, the final answer will be in centimeter cube, because that is the unit of volume, not GF. It's only numerically equal. Next, they've asked us to find the RD of the solid. Well, there we can use a direct formula, W1 upon W1 minus W2, and of course RD has no units. But in Roman number 3, they've asked us to find the weight of the solid in another liquid, not in water, but in another liquid whose density is 0.9 gram per centimeter cube. Now, we know that the weight of the solid in air is 32 GF. So the weight in a liquid will definitely be less than 32 GF. But how much will it be? First, let's calculate the upthrust exerted by the liquid, not by water, but by the liquid. And the formula for upthrust is V rho G, where V is the volume of liquid displaced, which is the same as the volume of water displaced, because the same object is being submerged in both. And both these volumes are indeed equal to the volume of the object. So the volume is same, whatever we calculated here, 3.2. Density of liquid is given 0.9, and G's value is always 1 in this chapter. So we get the upthrust by the liquid is 2.88 GF. So if the original weight is 32 and there is an upthrust of this much, then there will be a loss in weight. How much weight will appear to be lost? 2.88 GF. So what will be the new weight in the liquid? Clearly it will be the original weight minus the upthrust, which is 29.12 GF. Now, the 14th sum is similar to the Eureka idea which Archimedes got. You go to a jeweler who claims that he makes ornaments of pure gold, and pure gold's RD is known. It is 19.3. So he sells you a bangle weighing 25.25 GF. How can you be sure that's pure gold? Well, go home, immerse it in water and weigh it. Obviously, it will weigh less, 23.075 GF, because some upthrust will act on it. Now, using this W1 and W2 value, you can find the RD, because RD formula is W1 upon W1 minus W2. Substitute the values, shift the decimals, divide this. Do not copy from here. Come on, divide it on your own, and you'll get the answer as 11.6, which is far less than the RD of real gold. This proves that the gold isn't pure. And next, the 16th sum, which is IMP. There is a piece of stone whose mass is given in air. And then when you immerse it in a liquid, its weight is 10.9 GF, and in water it is 9.7 GF. So first of all, what is the weight of the piece of stone in air? Well, that is obviously 15.1 GF. If the mass is this much, the weight is also this much. Value of G is not given. Next, B. What is the volume of the piece of stone? Now, we've done some earlier as well. Volume of the stone is equal to volume of water displaced. And the volume of water displaced is equal to the weight of the water displaced, because density of water is 1. And weight of the water displaced is the loss in weight. So, by that logic, once again, we get the formula of volume as W1 minus W3. Note here, I cannot write W2 here, because W2 is actually the weight in liquid and W3 is the weight in water. So this way I can get the volume in centimeter cube. Next, what is the relative density of the stone? Well, the usual formula, W1 upon W1 minus W3. Again, I'm not writing W2 here because W3 has been used for water. W2 has been used for a liquid. So be careful about using the formula. So we get the RD. Clearly it's denser than water. And what is the relative density of the liquid used? Let's say it was oil or something. What is the relative density of that? Well, again, the usual formula, W1 minus W2 upon W1 minus W3. And we get the answer of the RD of liquid. Now let's move on to the next exercise, 5C. Mark the sum number 6 and 9 as IMP. The first sum. A rubber ball floats on water with 1/3 volume outside the water. Well, if 1/3 is outside, then how much portion of it is submerged? 2/3. So we'll use a formula here, which is small v upon capital V is equal to density of solid upon density of liquid. Note that small v is the part or the volume of the object which is submerged, and capital V is the total volume of the object. And the part which is submerged is 2/3, because in the question they have mentioned 1/3 of it is outside the water. So how much of it is inside water? 2/3. So we get V upon V as 2 upon 3. But we know the formula of V upon V is density upon density. So density of liquid, that is water, is known. So if you cross multiply, we get the density of the rubber ball as 2 upon 3, which is 0.67 gram per centimeter cube. Now in the third sum, there is a wooden cube of side 10 centimeter. It's a cube, so it's 10 by 10 by 10. And its mass is also given. What part of it will remain above the water surface? Well, let's understand this with the help of a diagram here. So the total length, breadth and height each is 10 centimeters. Even the breadth is 10 centimeters and even the height is 10 centimeters, even the length will be 10 centimeters. But we need to find out what portion of it is above the surface of water. First of all, let's find the density of this solid. Mass is given 700 and volume is also given indirectly because they've given the side and the volume is side cube. So we got the density of the solid. What about the density of water? That we know, it's 1. So now use the formula V upon V is equal to rho S upon rho L. Understand the small v is the submerged part and the big V is the full volume. Now isn't the submerged part a parallelepiped? That is, it has length into breadth into height to find its volume. So length and breadth and height is the same, or rather let's call it the h here. The height is unknown, it's definitely less than 10, and the length and the breadth are known, it's 10 by 10. So I substituted those values. H is unknown. What about the denominator capital V? That's the total volume, which is 10 by 10 by 10. So you cross multiply and you get the height. So this is the height, the lower portion, as 7 centimeters. But that's not what they've asked. They've asked for the part above it. So totally 10 minus 7 will give you 3 centimeters height above the water surface. Now the sixth sum. There's a piece of wood of uniform cross section. Its height is 15 centimeters. Well, it's a cube, so it'll be 15 by 15 by 15. It floats vertically with its height 10 centimeter in water and 12 centimeter in spirit. So that means it is submerging more in spirit. So what can you talk about the density of the spirit? It's definitely less than that of water. That is why the wood has to submerge more in the spirit to displace enough liquid whose weight is equal to its own weight. Only then it can float. So we have to find the density of the wood and then the spirit. First of all, drawing a diagram really helps in these sums. So this is in water, case 1. So 10 centimeters is submerged and totally it's 15 centimeters. We know that V upon V is density upon density. Small v in numerator is the volume of the submerged part, which is 10 into 15 into 15. And the total volume is of course 15 into 15 into 15. Density of solid, that is the density of wood, is unknown, but density of water is known as 1. So now cross multiply, and 2 upon 3, and 2 upon 3 is nothing but 0.67 gram per centimeter cube. But what about the second part, where it is submerged in a spirit? So again, draw a diagram. In the spirit, it is submerged by 12 centimeters and its total height is of course 15 centimeters. Again, we start with this formula. V upon V is equal to rho S upon rho L. Small v is the submerged volume. How much is the submerged volume? 12 by 15 by 15. And capital V is total volume, which is 15 by 15 by 15. The density of the solid, that is a wood, is known from the previous sum. Please take the fractional value, not the decimal value, because this is rounded off. So the density of the wood is 2 upon 3, and the density of the liquid, which is not water, of the spirit is unknown. So now you cross multiply this, you solve and get the answer of density of the liquid. Next, the 8th sum. The density of ice is given and that of seawater is also given. Find the total volume of the iceberg if 800 centimeter cube is above water. Well, if 800 centimeter cube is above water, then the part submerged will be very huge, because we know that only the tip of the iceberg is visible above the sea level. So what is the total volume of the iceberg? Let's start off with the formula. Small v upon capital V is density upon density. Densities are given. Solve it as much as you can. Now, what is the small v? It is the part of the iceberg which is submerged. That is the small v in the numerator. If the total volume is v, and out of that the top portion exposed is 800 as mentioned in the question. So what is the volume of the submerged part? Clearly it is v minus 800. We're talking about centimeter cube here. So instead of small v, now I wrote v, capital V minus 800. So now there is only one unknown variable in this equation. Cross multiply, open the brackets, rearrange the terms and get the value of v, and do this division right now. Do not copy. Do this division. You need practice in it. And don't forget the units, volume, so it is in centimeter cube. Finally, the 9th sum. Now, as we read the question, we should jot down the data. And for this sum, I'm going to draw a diagram. What they have given is, I'm reading the data simultaneously. The weather forecasting plastic balloon of volume 15 meter cube. So see here, I wrote here, volume is 15 meter cube. This is the volume of the hydrogen in the balloon. You can even say it is the volume of the air displaced by this balloon. Next, the hydrogen is of density 0.09 kilogram per meter cube, mentioned here. The volume of the equipment is negligible. So compared to this volume of the balloon, the volume of the equipment is not important. So we can ignore it for now. Now the mass of the empty balloon was 7.15 kg. The empty balloon. It seems to be a very huge balloon. And also the density of air outside is given as 1.3 kilogram per meter cube. So Roman number 1, how will you find the mass of hydrogen of the balloon? Well, that's pretty straightforward. Mass is always volume into density. Volume we know, it's 15 meter cube, and density also is given. So we get the answer of mass of hydrogen 1.3 kg, 1.35 kg. But understand that I could have even written this as weight of hydrogen as 1.35 kgf. It's the same thing here. Now, mass and weight are numerically equivalent. Next, what is the total mass of the hydrogen plus the balloon? Well, hydrogen's mass we found out and balloon's mass is given. So we just add it and we get the total mass. To this, What if we add the mass of equipment as mentioned in the question? Yes, please read the textbook also. Always read carefully. So mass of equipment is taken as x. We don't know it. So now the total mass is this. That is the balloon plus the air plus the equipment is this. Now, if you notice, this entire balloon and the equipment is submerged, if I can use the word, submerged in air. It has displaced air. So the weight of the air displaced will be equal to the entire weight of this equipment. Or we can even say that the mass of the air displaced by it is equal to the mass of hydrogen plus balloon plus equipment. That's why it is floating. Whenever something is floating, the weight is equal to its own weight is equal to the weight of the air or the fluid in which it is floating. So let's find the mass of air which was displaced by it. The mass of air displaced is volume into density. Volume is the same, 15 meter cube, and density is given as 1.3. So we get the total mass of air displaced is 19.5. But according to the law of flotation, the total mass of the object should be equal to the mass of air displaced. That's why it is floating. So substituting the values, we get the value of x. This means that the mass of the equipment is 11 kg, because anything more than 11 kg, it cannot float, it will sink.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.